How do we find the area under a curve? Instead of counting blocks, we slice it into rectangles. Each rectangle has a height of f of x and tiny width dx by adding them all from x is equals to a and x is equals to b. We use integration. Area is equals to the integral of f of x times dx. And that's how we can get the exact area under a curve. And now, let's go on for our examples for better understanding. But before we dive in, hi, I'm Hart and I'll be your guide as we explore the core ideas of integral calculus. Whether you're viewing for a test or learning this concept for the first time, this tutorial is made for you. So grab your notebooks, take a deep breath, and get ready to master the math. So we have here a curve, and as we can observe, this shape don't have a specific formula for area, unlike the polygons. So what we are going to do is to think what shape can we make here that has a formula for area. So we can approximate this with a shape that we can get the area of. So what do you think that shape may be? It's rectangle. So if we cut this curve into strips and use integration to sum it up, we can get the area. So this plane has a thousands or millions of strips. So how did we come up to this formula? So we know that the integral is used to add tiny pieces to find the whole of something. So since we use tiny rectangles under the curve to estimate the area, we need to sum indefinitely many of these rectangles. So where did the YH minus YL dx came from? So we know that the area of a rectangle is equals to base times height. So the YH minus YL is the height and the dx is the width of our strip here. So our dx is over here. Since we use integration, we have to make this dx. So our YH or Y high is this y is this one, this line, this is the Y high, and then this one here from the bottom of the rectangle up to the x-axis, this is the Y low. So if we subtract this one, these two, we can get the height of the strip here. So that is where the formula is coming from. So of course, since we use the infinite integration, we have to put limits. So our plane is from here to here. So let's make this A to B. And what if our strip is horizontal? So let's say if our strip is like this, and then we make our strip horizontal like this. So since it's horizontal, our thickness is what? It's dy, because our reference axis is y-axis, and then our base is x right, this this line is the x right because it's here at the right, and then our x left is this one. So it's the same as the first graph. So we have here a example, y is equals to x squared and y is equals to 4. So we know that when the variable is squared, it has 2x, right? 2x. So for us to get the values for the vertices, we need to equal these two. So if y is equals to x squared, and then we know that the y is equals to 4, so 4 is equals to x squared. So if we square these two, if we get the square root, this will be cancelled, right? So x is equals to positive or negative 2, right? So if we have here 1, 2, 2, and then our 4 is 2, 4. So if we graph that, we will have something like this. Wait, our drawing is not that accurate. So again, what is our first step? We will cut this into strips, right? And then this will gonna be dx, since our reference axis is x. So wait, so this line is y is equals to 4, and this line y is equals to x squared. So this is our y low, and this is our y high. So again, what is our formula? So our formula for area is area is equals to integral of y high minus y low times dx. Then our limit is, since it's x-axis, our limit is also from the x-axis. So from 0 to 2. So from 0 to 2. So now let's put our values. So integral from 0 to 2. So our y high is 4. So it's 4 minus y low is equals to x squared. So x squared dx. And now we are going to integrate. So the integral from 0 to 2. So what is the integral of 4? It's 4x, right? Minus the integral of x squared, which is the power formula, 1/3 times x cubed. Oh no. It should be limit from 0 to 2. And now we are going to put the limits on here. So that is equals to 4 times 2 minus 1/3 2 cube minus, we're done with 2, now we put the 0. So 4 times 0 minus 1/3 0 cube. So we know, since it is 0, this is cancelled. So we don't have to put this 1. And then this is equals to 4 times 2 is 8 minus, what is the cube of 2? That is 2 times 2, 4 times 2, 8. So 8 all over 3. 8 all over 3. So this is equals to 8 times 3, that is 24. 24 ba ito? It is 24. 8 plus 8, 16. So 24 minus 8 all over 3. So 24 minus 8, that is equals to 16. So our area is 16 over 2 square units. So this is our area. What you are seeing here is a 3D object slowly rotating in space. This object represents a volume generated by revolving two-dimensional shape around the axis. In calculus, we use integration to calculate the volume such solid. Specifically, this is similar to a disk or washer method, where we sum infinite number of thin slices. Each horizontal cross-section you imagine here corresponds to a slice like a disk with a certain radius. The area of each slice contributes a total volume. As the model spins, we get a clear view of how these slices stack together. When integrated along the axis, this forms a solid three-dimensional figure. This technique is essentially what volume by integration represents, taking an area function, rotating or stacking it, and using calculus to sum all those infinitesimal volumes. The smoothness of the shape illustrates how continuous functions generate continuous solids. This is the geometric result of integrating over a range. Whether you're using disk, washer, or shell, the principle is the same. Summing up infinitely many infinitesimal volume gives you the whole. Now let's take a look of this sample for better understanding. So for our next example, we have the volume by integration. So we have the same example so that there will be no confusion, since we only perform a one example per topic. So in order for us to get the volume of this plane, we need to revolve it around the axis. So why do we need to revolve this? Because as we can observe, the region that we have is only 2D. And we know that for us to get the volume, we need a 3D solid. So now let's revolve this plane. So if we mirror this out, if we mirror that, we will revolve it. So let's say we will revolve it in the x-axis. So here we will have a revolve it here, revolve it. So if we cut this plane into strip like this, so let's redraw it. So we will have something like this. If we cut that into strips, something like this. Like that. So we have a hole here. So what is our formula for volume? So we know that the volume is equals to, if volume of a circle, we will be having a pi r squared. But since we use the integration, we will integrate this pi r squared from a to b. So since our plane region has a hole, we calculate the volume of the outer part. The outer part, this one, the outer part, this one, from the center. We calculate the volume of the outer part and subtract the volume of the inner hole. So this one. Also from the center. So, this figure is called a washer. So, if we put that into the formula, we will get the volume, the integral of pi r's, let's call this r, and this one is a small r. So we will have a pi r squared minus pi small r squared. And since our strip is dx, we'll put here dx, or the thickness. So we can factor this out. So this will be equal to integral of pi times r big R squared minus small r squared dx from A to B. So this is our formula for the volume. So, wait. Let's place this. Our formula is volume is equals to the integral. Let's put the pi outside since it's constant. The r big R minus small r squared times dx from A to B. Now let's get the values. So let's put the pi. So what is our pi? What is our radius or outer radius, or the big radius? So as we can observe here in our figure or the graph, the r is from here to here. So as we discussed earlier in area, this y here is y high, right? And then this one here, if we put it into strips, wait, like that. This one here is the y low. So again, our y high is y is equals to 4, and our y low is y is equals to x squared. So now let's put it into the formula. So our ry is the y high squared. So 4 squared minus y low, the x squared times the dx. And then our limit is from, since we revolve it in the x-axis, our limit is also from the x-axis. So from 0 to 2. 0 to 2. So now that is easy now. So pi. So now let's integrate. So pi times, what is the integral of 4 squared? So 4 times 4 is 16. So this is 16x minus, this will become x to the fourth. So what is the integral of x to the fourth? That is 1/5 x to the fifth, limit from 0 to 2. And now let's put the limits. So pi times 16 times 2 minus 1/5 times 2 to the fifth. So let's use our calculator. So 16 times 2 minus 1/5 times 2 to the fifth power. So this is equals to 128 all over 5 pi. So since this is 0, we don't have to put this, so because that is already cancelled. So this is our volume, cubic units. So if you want to make a shortcut on your calculator, what you need to do is the integral. So 4 squared minus x squared from 0 to 2. So that is 128 all over 5 pi, since I didn't put the pi here. So yeah, we are good. So for our next topic, the centroid. So we still have the same problem, so that there will be less confusion, because if we use a different problem, there might be a confusion. And so we still have here y is equals to x squared and y is equals to 4. So in solving the centroid, we have the formula of total area times y bar is equals to the integral of distance times the integral of area. So our d is the distance from the center of the strip to the axis. So let's rewrite this off here. So if we make a strip here, our d is equals to from the center up to this axis, up to our reference axis, and the AD is the differential area. So the D here, this is the D. The D is the average of the height of the strip, or we can write it as, so if we get the average of the height, we can get y high plus y low all over 2. So this is our average of the height. And our area, as what we have discussed, the base times height, or the let's rewrite this one. So y high plus y low all over 2 times the area. In our previous discussion, this is y high minus y low, or the base times the height times the base dx. So of course we can't forget the integral. Let's just put here the 1 all over total area, so that this will be by y. And now we have the formula for the centroid of y. So, since we have here the dx, our reference or our limit is the x1 to x2. So this is just the same if our reference axis is the y-axis. The only difference is that we will make it x right plus I plus x left all over 2 times x right minus x left dy. So this is x bar from y1 to y2. So 1 all over total area. So the objective of the centroid is finding the center, or to locate the center where the balance point is. Yes. So now let's solve this one. Let's erase it first. So first, let's solve for the y bar. So if we plug in our equations, our given, this is equals to, since this is dx, from 0 to 2. Our y high is this one, right? Y high, y low. Same as on our previous discussion on the area and the volume. So y high is equals to 4. So 4 plus y low x squared all over 2 times y high minus y low, so 4 minus x squared dx. Don't forget the 1 all over area. So what is our area in the our example earlier? So it's 16 all over 3. So we will put 16 all over 3, or we just put here 13 all over 16. Yeah. So for us to get the y bar, we use our calculator. So integral of 4 plus x squared all over 2 times 4 minus x squared times 3 all over 16. 3 all over 16 from 0 to 2. So our y bar is equals to 12 all over 5. So let's put it here. So our y is equals to 12 all over 5 y bar. And now let's solve for the x bar. So let's erase this. So again, our x bar is equals to 1 all over area, total area, from y1 to y2 times x right plus x left all over 2 times x right minus x left dy. So we need to get the value in terms of y. So we can get it here. So if we get the square root of both sides, we can get x is equals to the square root of y. Right? So if y is equals to x squared, so x squared equals to 4. So our x here is equals to 2 since we squared both sides. So our our x right is this one and our x left is this one. So let's plug it in our formula. So our area is 3 all over 16. It's integral from 0 to 4. So what is our x right? That is 2 plus the square root of y all over 2 times 2 minus square root of y dy. So our x bar, so let's use our calculator na lang. So this 3 all over 16 times 2 plus the square root of y. Let's use the x all over 2 times 2 minus the square root of y from 0 to 4. So our x bar is 3 all over 4. 3 all over 4. So our centroid is equals to, the vertices of our centroid is 3 all over 4 and 12 all over 5. So if we plug it to our graph, so our x bar is equals to approximately 0.75. So let's say over here, and our yes, and then our y is at 2.4, so somewhere here. So our centroid is over here. This is our centroid.
What you are seeing here is a great example of moment of inertia. It's all about how an object resists changes to its rotation, depending on how the mass is spread out. Some objects are easier to spin, while others take more effort. In this case, you can really see how the distribution of mass affects the motion. It's not just about the weight, but where that weight is placed. That's the key idea behind the moment of inertia. And now let's go to our example for better understanding.
So for our fourth topic, we have the moment of inertia. So again, let's use our previous example so that there will be no confusions. So again, this is our parabola. This is the curve where this is equals to 2 and this is 4. So in moment of inertia, we have the formula. Inertia is equals to the integral of distance squared times the differential area. So why we use the squared? Because the farther parts affects the rotations more. So the values are just the same with the centroid topic. D is the distance from the axis to the center. If we put a strip, so this is dx. We put a strip, so let's put this up. This is the integral of y high plus y low over 2 squared times y high minus y low dx. This is the area, this is our distance. So our limit is, since we are dx, our limit is from 0 to 2. Now, we will put our values. So here, this is our y high, which is y is equals to 4, and our y low is y is equals to x squared. So this is strips. So now we plug in. So this is 4 squared plus x squared square all over 2 times y high, that is 4 minus x squared dx from 0 to 2. So our I is equals to, let's just use the calculator. So this is, so the 4 squared plus x squared square all over 2 times 4 minus x squared from 0 to 2. So our moment of inertia about x is 46.32. So this is our moment of inertia. So the last topic, we have the work. So in work, we are finding out how much effort it takes to make a work done. So for example, we have here a water tank filled with water. We want to know how much work is needed to empty this tank by pumping here. We need to use the integration because our height is changing as we pump out the water, right? So our formula for this is work is equals to the integral of force times distance. Here, our force is the unit weight of the water. So our force is the unit weight of the water times the area of the tank. So area times the area of the tank and the thickness of the strip. So we called it dy. This is our force. And then for our distance, so let's bracket this. So our distance is the overall height of where the water will travel minus the distance from the bottom of the tank up to the center, or the height minus bar y. So let's discuss this one by one. So we know that the unit weight of the water is 9, 8, 10. Why? Because the density of the water is 1,000 and times gravity 9.81. So that is how we get the unit weight of the water. So we multiply this by the area. So since we have a circular here, so our area is equals to pi r squared, which is our r is equals to 1. So 1 squared. And then since our height here is changing, means our dy is the thickness is dy. So let's say we have here the centroid and we cut this into strips. So this is dy. This is our radius. So let's put dy. This is our force. And then for our distance, so what is this distance? This is y, right? Because it's vertical. And then if we, wait, if we add this height, this is equals to 7, right? So let's call this y bar. Am I doing this right? So, yes. So, our distance is equals to, we are finding the distance from the centroid up to the top where our water will travel, or where it will pump out. So, for us to get this distance, we need to subtract the overall height minus the y. So, this is 7 minus y. Wait. No, this is the height. I'm sorry. This is the height, and this is the y bar. It's equals to y. So let's put it here. So that is 7 minus y. So our limit is, since we use dy, our limit is also from the y-axis. So for example, we have here, so this is our y, this is our x. So our limit is from the bottom of the tank up to the height of the tank, since our water is only in here. So our limit is from 0 to 5. So now let's use our calculator to get the work here. So 9, 8, 10. Oh, let's put it outside because it's constant. So 9, 8, 10 pi times integral of 1 squared times 7 minus y, or let's make it x, dx, from 0 to 5. So our work is 2,20725 pi. So this is the work that we need, or the effort that we need for us to empty this tank filled with water. So that's